Hi there, guys. So in the last exercise, 14b, we were testing for whether or not the binomial distribution had a different parameter to 0.5. Okay, so we knew that we had a binomial distribution. We knew it because there were 20 trials and each one of them had either success or failure. We were testing the tastiness of a certain type of cheese. Okay, so in this one, we're going to test whether or not the parameter behind the Poisson distribution is correct or not. So we know that this information should follow a Poisson distribution. We think that it has particular underlying characteristics from potentially some previous research. Now we've done some new research and we're going to test to see whether or not there's a change in the parameter being the mean or the variance, that lambda, or I think alpha they were calling it in chapter 13 or unit 13. Okay, one extra thing as well is that lots of these tests can be done on your calculator. These ones for the binomial and the Poisson distribution at the moment can't be done on the calculator. There is no test for this. You just need to find the critical region, or you need to find the p-value. So that's what we're building up to in these questions. Okay, so let's have a look at this. Let's just recap on what it says. It says if a Poisson distribution is known, if a distribution is known to be Poisson rather, or if it has the characteristics of a Poisson distribution, a hypothesis test can be done to test for a particular value of the mean. So we're checking for the parameter lambda or alpha or mu, if you like, in this case. Right, let's get rid of that. Let's do this through the question. Should be fairly straightforward given the last one, if you put the effort into the last video or the last exercise. So let's look at this one. It says the number of cars passing a school between 1 p.m. and 1:30 p.m. on a weekday can be modeled by a Poisson distribution with a mean of 32. So we already have some existing research that says that this is true. This is the null hypothesis. Then something's changed and we're collecting more information and we need to check whether or not things have changed really or not. So it says a set of traffic lights is installed at one end of the road and it is hoped that this will reduce the number of cars that use this road. A teacher records the number of cars that pass between 1 p.m. and 1:30 p.m. on 5 days, so not just on one day, during a school week. Now, remember, of course, that the Poisson distribution is scalable. So if you would normally get 32 cars between 1 and 1:30 p.m., obviously the teacher is trying to get slightly more data. We know that this is the original hypothesis based on potentially thousands of bits of information. Potentially somebody has sat out on lunchtime after lunchtime over the last 5 years to collect this data and find this mean. But this teacher only has 5 days to give up his lunch for this, or her lunch for this. So we're looking for cars that pass for 5 days, but we would expect that to be 5 times 32. Okay, so 160 cars is what you would expect the mean to be using the null hypothesis. So it goes straight into the question here, find a critical region for a test at the 5% level. Now, you always start by writing down what your hypotheses are. Okay, so what are your hypotheses here? Well, we've got x, which is what they're defining this variable to be, should follow a Poisson distribution with a parameter, or a mean, or lambda, or alpha of 160. Now that's H0 and H1. Oh, sorry, no, it's not. That's the original distribution. H0 is saying that, what are they calling it? Lambda? No, they're calling it mu. Okay. So mu is equal to 160. And H1 is saying that mu is less than 160. We are expecting this to be a one-tailed test. Now, a two-tailed test is saying we don't really have an idea, we just want to know if it's changed, in which case you will have to look at either end of your distribution to find 5%, or for those critical regions. Now that's slightly more difficult, and we'll deal with that when we come to a normal distribution. However, in this case, we're just looking to check whether or not the traffic has reduced. So we want to know, we suspect that the traffic has gone down, and so we want to check whether or not the lights has made any difference. So this is a one-tailed test. We want to check whether mu is now less than 160. So our alternative hypothesis, that's H1, is such that mu is less than 160 here. Now, we always write that down to start off with. That's what they've written down here as well. Okay, so let's just take some of this back. Okay, so I would state distribution, state your test. That's essentially what they've done there as well. Now, we haven't found the critical region yet, but before we go into that, let's just show you what I've done here. So on Excel, I came up with a quick PDF and CDF for Poisson distribution. And I came up with numbers from 0 down to 500 and something, and then I just stopped. I could have gone on longer, but you can see what happens to the PDF in this case. When I get to 500, probabilities become extremely small there. In fact, for 160, for a Poisson distribution with 160, where these cars are assumed to turn up randomly within that interval, you can see that the most likely number that we're going to get is 160, with a probability of about 3%. And then it tails off on either side, so that we would expect at least 100 cars to be passing and no more than 200 cars passing in an hour if it is genuinely following that Poisson distribution during that time period. Okay, so how did I make this one? Just quickly, I came up with my parameter there, 160, and I put in Poisson distribution B4. That's this one here, so that's my X value. My mean, which was fixed at the top here, fixed with some dollar symbols at B2. And did I want cumulative or not? I didn't want cumulative. I wanted PDF rather than cumulative. So I went with 0. If I wanted to go with cumulative, I would have to say 1, as in true. Okay, now with the next one, I came up with, with the next one, I came up with, I could have done CDF here. I didn't know. I just did a sum of my PDF. Okay, that's an alternative way of doing CDF, of course. Starting with the first one and summing the second one and so on. So the first one was summing from C4 to C4. The next one was, because I fixed C4, the C4 to C5 and so on. Okay, now I've plotted both of those graphs. I simply went to this graph here, I think, insert a bar chart, column chart here. And so that's what I did. And there we go. That's what you can see it turning up as. There's a PDF, and I didn't label this one CDF, but I could have. Because in fact, if you can see on this one, this goes up to 100%. So CDF will obviously get to a point where the chance of having, say, for example, the probability of getting 270 cars or fewer is going to be 1, or practically 1. So close to 1 that it's almost infinitely small as to the difference there. Okay, now you can actually see the original distribution is hidden there because I plotted both of those, PDF and CDF, and you can see the PDF distribution is hidden there. These heights are actually really small. This height goes up to 1. This goes up to 3%. Okay, so let's go back to this. You probably skipped ahead on that. Let's go back to this. Okay. So what do we need to do? We need to find the critical region for the test at the 5% level. So we basically want to find the first value for which we're saying, what's the first value for which the probability X is less than or equal to that value. Okay, so perhaps we can call that R or something, is less than or equal to 5%. So that's what we're looking for here. Now, again, I would do this via some trial and error here. I would realize that 160 is clearly the middle, and so I just need to go a little either side. So I might try, I don't know, I might try 140, I might try 150, I might try 130, and I'll quickly get there on my calculator. So I'm looking for the first time at which my value for my CDF for the Poisson distribution dips below 5%. 1 second, somebody at the door. Just going to pause this one off. Sorry about that, just getting the microwave fixed. Okay, right, so we're looking for the first time when x is less than or equal to a particular value, dips below 5%. Now, you can see from the book that they're giving you this little chart here. And again, you could make up a chart on your calculator. And you can see that you've got percentages leading up, building up to 5%. And we're looking for that first value where we're getting a value which is below 5%. We don't want to be above 5%, otherwise it's not a 5% significance level test. Okay, so 138 is our answer. Now, how do we get that? Well, for me, I'd do some trial and error. I'm also just going to show you the PDF and the CDF I did on Excel. So again, same thing here. If you look at the CDF, we're looking again for getting 5% in this region this time, not on this end, because we suspect that we've lowered the amount of traffic. So in scanning down here, we can see we've got extremely small values until we get to about 115. And there we go. First time we're hitting 1% is 131. And 138 cars, according to the original null hypothesis, at 138 cars, we're just under 5%. And we're over 5% at 139. So 138 or below, if that's what the teacher records in that week, then we would accept the alternative hypothesis, because 138 is the critical value for which we would accept the alternative hypothesis, and 138 is in the critical region. Okay, and 139 is no longer in the critical region. Okay, so how do we do it on the calculator? Well, let's just try it out on the calculator as well. So again, I'm going to go to calculate, I'm going to go menu, I'm going to go probability. So probability, which is 5, not 6. So probability on the TI Inspire. I'm going to go distributions. I'll go Poisson CDF. So that's K. And I'm going to put lambda in as 160. My lower bound is 0. My upper bound is going to be, I don't know, 140, 150, and so on. Let's try 150. Let's press OK on that. And I'm quickly getting out 23%. So I can see that's way too high. So I'm going to do this via some trial and error. So again, I can do Control Copy. I can do Control Paste. And then I'm going to just change that quickly from 150 to 140. Oh, I can see that that's 6%. So I need to go a bit below that. So again, I'm going to try 139. And I can see I'm still just slightly above 5%. So again, I'm going to do that same thing again, Control Paste again. And I'm just going to put in 138. And there we go. That's as long as it should take. That took about 40 seconds or something. And we're now at underneath 5%. So 138 is the critical value. All I'm doing is copying and pasting my Poisson CDF from the book. Now let's from the Scratchpad. Now let's just have a look to see if there's an inverse Poisson distribution. No, there is not. So on my calculator, there is not an inverse Poisson distribution. So you will need to do this by either trial and error or by creating a table, which the book shows you how to do as well, if you want to. From my point of view, I would just do this by trial and error. I think there's less chance of you making mistakes through trial and error as well. Okay, so critical region is less than or equal to 138. Right, so part B, let's push on. Part B, if the total number of cars is 140, state if there is evidence at the 5% level for the number of cars that the number of cars has been reduced. So although we can see that the number has definitely gone down from what we would expect as 160 to 140, we can't say at the 5% level that this is significant. This may just be random chance. Maybe we should go back and do more tests to see if this is going to be the case if we did it for another week, for example. But at the 5% level, 140 is not, it gives us a p-value which is greater than, so there's the p-value, gives us a p-value which is greater than 5%. So at the 5% level, we could not accept that this is any different than some random chance with the original distribution. Okay, let's see what they're saying. So it says here that 140 is greater than or equal to 138, so it's not significant. Okay, so the way in which they've done that is via the critical region test. So they've done it through the critical region. Given that we know that the critical region is less than or equal to 138, since 140 is not in that critical region, therefore it's not significant. Therefore, there is insufficient evidence at the 5% level to reject the null hypothesis. Okay, however, Part C shows us the other way of doing this. And it says here, find the p-value for the test, for a test statistic of 140 cars, and use this to verify your conclusion to Part B. So all they're really asking there is they're saying, okay, well, what's the probability that X is less than or equal to 140? That will give you your p-value. So that is the p-value. And you will find out, of course, that that is greater than 5%. And of course, actually, here's the value. So again, let's just see what they've said here. Let's rub this one out. They said there 0.592, 0.0592 rather, and that is greater than 5%, hence it is not significant. So there's the two methods there. Either you can say, are we in the critical region? If we're not in the critical region, then we still accept H0. We do not have enough evidence to reject it. Or you can just work out what's the probability that X is less than or equal to 140, which obviously is the easier method here. And the fact that that's above 5% means to say that it's not significant. Now, that's the easier method. But if the question asks you to find the critical region, then the question will lead you through that method. So you need to know about that as well. Okay, guys, well, good luck with the exercise. Thank you for listening. And the next section is not actually the normal distribution hypothesis testing, which would be normal in a book. It is a test for the product moment correlation